In this lesson, we will complete our study of Global Navigation Satellite Systems, GNSS. First of all, we will look at the basic principle used in GNSS, namely, the determination of range from the time travel of radio energy. With very accurate timing, the range of the receiver, the aircraft, from the transmitter, the satellite, can be established with minimal error. Time is computed in 3 separate timing references. These are SV time, GPS time, and UTC. SV time is the time maintained by each satellite. Each satellite contains 4 atomic clocks, 2 cesium and 2 rubidium, which control the satellite's transmission accuracy better than 1 nanosecond or 1,000 millionth or 1 billionth of a second. SV clocks are monitored by the Master Control Ground Station and are occasionally reset to maintain time to within 1 millisecond of GPS time. Clock correction information is passed from the master station via satellite to the user to correct for any residual SV timing error. Since the aircraft equipment also needs to know the start time of the transmission, it requires its own clock. This clock is not as accurate as the satellite's atomic clock, but this problem is resolved as part of the signal process, and SV time is converted into GPS time. GPS time is measured in weeks and seconds from midnight, January the 5th, 1980, and it is corrected to within 1 microsecond of UTC. UTC time is then computed from GPS time using the UTC correction parameters sent as part of the navigation message. The navigation message is contained in 1 frame comprising 5 subframes. The subframes each take 6 seconds to transmit, so the total frame download time is 30 seconds. Each frame starts with 2 words. The first, the telemetry word, is a preamble to the data that follows it. The second word, the handover word, states the SV time, so every line of data starts with SV time. Frame 1 contains SV clock error. Frames 2 and 3 contain the SV ephemeris, that is, its orbit parameters. Frame 4 contains data on the ionospheric propagation model, GPS time, and its correlation with UTC. The 5th frame is used to transmit current SV constellation almanac data. A series of 25 frames is required to download the whole almanac, which is usually done hourly and is valid from 4 hours to several months, depending upon the type of receiver. Because the orbits are mathematically defined, an almanac of their predicted positions can be maintained within the receivers. Thus, when the receiver is switched on, provided it knows its position and time to a reasonable degree of accuracy, it will know which SVs to expect and can commence position update immediately. If the almanac is corrupted, out of date or lost, or if receiver position or receiver clock time are significantly in error, the receiver will not find the expected SVs and will download the almanac from the constellation. The almanac data fills 25 frames, so it takes 12.5 minutes to download. The receiver will now carry out a sky search, which involves the receiver checking which SVs are above the horizon and selecting the 4 to give the most accurate fix, then commencing a position fixing. This takes, at the least, a further 2.5 minutes. Hence, the time to first fix will be at least 15 minutes. If there are no problems, then the first fix, on initialization, will be obtained within about 30 seconds. How is the time taken for the message from the satellite to the receiver message measured? Unlike radar, where a signal is transmitted from the ground and the time taken for it to return is measured, there is only a one-way transmission, and it is from the satellite. The receiver generates its own internal digital code, which is identical to the coarse acquisition code transmitted by each satellite. These long and complex codes, which appear random but are actually repeated patterns, are known as pseudo-random. If the satellite transmission and the internally generated code started at the same time, the time difference between the end of the internally created code and the receipt of the end of the satellite code could be measured exactly. As the speed of radio wave propagation is known, namely 3 × 10⁸ meters a second, the observed delay in receipt of the satellite signal can be converted into the distance that the signal has travelled. This will be an error by the difference between the receiver clock and the satellite clock, and so will not be the accurate range. We call this the pseudo-range. How this is corrected will be explained shortly. To calculate its position, the receiver uses 4 SVs and constructs a 3-dimensional fix using the pseudo-ranges from the 4 SVs. Each range corresponds to a position somewhere on the surface of a sphere with a radius in excess of 10,900 miles. The intersection of 2 range spheres will give a circular position line. A third range sphere will produce 2 possible positions for the receiver, one near the Earth and the other out in space, which is obviously not the position of the receiver. So, it would be possible to use 3 pseudo-ranges to produce a position. However, a 4th range sphere is needed in order to produce a single position. As we said earlier, the receiver clock is not as accurate as the SV clock. Therefore, it is unlikely to be perfectly synchronized with it. This desynchronization, or clock bias, means that the range calculation will be erroneous, which is why it is referred to as a pseudo-range. The receiver clock is deliberately kept in error by a small factor to ensure that the correction process can only go in one direction. As a result, the position lines will not meet in a point, but in a cocked hat. So, when the receiver sets about calculating the correct ranges, it knows that it must reduce the pseudo-ranges. All GPS errors are stated at the 95% probability level. That is, 19 out of 20 times, the accuracy will be within the stated limits. Of course, it also means that once out of 20 times, the limit will be exceeded. Ephemeris errors in the SV's calculation of position are caused by the gravitational effects of the Sun, Moon, planets, and solar radiation. The SV position is checked every 12 hours. The 95% error is 2.5 meters. SV clock error is also checked every 12 hours. The error is 1.5 meters. Ionospheric propagation error occurs because the ionized particles in the ionosphere cause the radio energy of the satellite transmission to be slowed down. This is dependent upon the level of ionization and the frequency of the radio waves. The higher the frequency, the smaller the delay. The higher the ionization, the greater the delay. The receiver contains an average model of the ionosphere, which is used to make time corrections to the measured time interval. The ionospheric delay is inversely proportional to the square of the frequencies used by the satellite. As two different frequencies will experience different delays, by measuring the difference in the arrival time of the two signals, it is possible to deduce the total delay experienced, hence minimizing the error. The error for single-frequency operations is 5 meters. Tropospheric conditions can affect the propagation of radio waves. So, pressure, density, temperature and humidity all have to be taken into account. Internally generated receiver noise can affect accuracy by 0.3 meters. Multi-path errors caused by reflections from the ground or parts of the aircraft can cause errors of 0.6 meters. Geometric dilution of precision, or GDOP, between position lines occurs when satellites are close to each other. The ideal satellite configuration for minimum dilution of precision is one satellite directly overhead and 3 others on the horizon and spaced at 120 degrees. There used to be an intentional error introduced by the United States Department of Defense called selective availability. Its purpose was to deny a potential enemy the extreme accuracy afforded by GPS by introducing random errors, known as dithering the SV clock time. It was about 100 meters. This has now been removed, and it has been stated that it will not be reintroduced, as the US can now switch off the signal at will over selected parts of the world. The accuracy required by ICAO is plus or minus 13 meters in the horizontal, plus or minus 22 meters in the vertical, and 40 nanoseconds in time. If the SV information degrades, the GPS receiver has no means of determining the degradation. Differential GPS, or DGPS, is a means of improving the accuracy of GPS by monitoring the integrity of the SV data and warning the user of any errors which occur. There are 3 types of DGPS in use or under development: air-based augmentation systems, ABAS, ground-based augmentation systems, GBAS, and satellite-based augmentation systems, SBAS. The air-based augmentation system is called Receiver Autonomous Integrity Monitoring, or RAIM. RAIM requires 5 satellites and is then able to identify which space vehicle is in error. Let's see why it's 5. 1 satellite gives you accurate clock time. 2 give you a single position line. In reality, they would be curved ranges, but we're drawing them as straight lines for simplicity. 3 give you a 2-position line fix, but no cross-check. 4 give you a 3-position line fix. The third one would give you 3D fixing. But what if one of them is in error? You're going to get a large cocked hat. RAIM will not permit you to use this fix. With a 5th satellite, we get 4 lines. The erroneous one can be identified. This is the minimum basic RAIM. With 6 satellites, you still have RAIM, even if you lose one. This is the mandatory minimum requirement for an IFR installation. The ground-based augmentation system is implemented through a local area augmentation system, LAAS. The system provides both failure warning and enhancement of the GPS receiver position by removing ephemeris and SV clock errors and by minimizing tropospheric and ionospheric errors. It is specifically established to provide precision runway approaches. LAAS requires a precisely surveyed site on the aerodrome. A GPS receiver on the site compares this known position with the position received from the GPS. The error in the X, Y, and Z coordinates is determined, and a specifically formatted message is transmitted to aircraft close to the aerodrome. The aircraft interprets this as a transmission from a space vehicle on the aerodrome, known as a pseudolight. When the aircraft is close to the aerodrome, the DGPS site, the ionospheric and tropospheric conditions will be virtually identical, and therefore these errors are eliminated. LAAS has the potential to achieve Category 3C type operations. Satellite-based augmentation systems operate over a wide area and are known as WAAS Wide Area Augmentation System. Ground reference stations, spread over many countries, operate on precision-surveyed sites so that they can compare this position with the GPS position and determine the SV range error. At present, only one satellite system, EGNOS, is operational. This is the European Geostationary Overlay System. The range error is transmitted to geostationary satellites in the East Atlantic and Indian Ocean, in Marsat, which then transmit it to users who use the information to correct their GPS position. WAAS is not as accurate as LAAS, and it is unlikely to achieve the accuracy required for Category 1 operations. Two other WAAS systems are likely to emerge shortly. One is a Japanese system called MSAS. The other is Indian and is called Gagan. This will be a long summary because we are going to bring together the most significant points from the last two lessons. Firstly, let's remind ourselves of the specification and characteristics of the three systems presently complete or near completion. All of these use 3D Earth-centered, Earth-fixed coordinate systems. A GPS fix gives latitude, longitude, GPS height, and time. There are three segments. The space segment is the constellation of satellites, otherwise known as space vehicles or SVs. The user segment comprises all the receivers designed to receive and decode the GNSS signals. The control segment is the master control, backup control, and the network of worldwide monitoring systems. It monitors the satellite positions, clock time, satellite health, and ionospheric conditions. There are three standards of time used in GPS. The satellites all have highly accurate atomic clocks, internally correct to within plus or minus 1 nanosecond. They are kept within 1 millisecond of GPS time. GPS time does not coincide with UTC. The difference is contained in the navigation message. Finally, there is UTC, which is the time actually displayed to the user. All of the systems have at least two frequencies. In the case of GPS, these are L1 and L2. L1 is available to all users, and carries the CA codes and the P codes. L2 is available to authorized users only, which, broadly, means military forces. It uses P and PY codes. GPS nominally offers two grades of service, standard and precise. However, selective availability has now been removed, so all users get the precise service. Pseudo-random codes identify the satellite and provide the time using code correlation technique. The range is the time between the satellite signal and the receiver signal codes times the speed of electromagnetic waves. The navigation message contains the SV time of transmission and clock error data, space vehicle ephemeris data, orbital information, ionospheric propagation correction data, health and status of SV, almanac data for the constellation, and other general data. If the ephemeris data is wrong or not immediately available, the navigation message takes 12.5 minutes to download. The time to the first fix may be in the order of 15 minutes. RAIM stands for Receiver Autonomous Integrity Monitoring. One satellite gives you accurate clock time. Two give you a single position line. In reality, they would be curved ranges, but we're drawing them as straight lines for simplicity. Three give you a two-position line fix, but no cross-check. Four give you a three-position line fix. The third one would give you a 3D fixing. But what if one of them is in error? You're going to get a large cocked hat. RAIM will not permit you to use this fix. With a fifth satellite, we get 4 lines. The erroneous one can be identified. This is the minimum basic RAIM. With 6 satellites, you still have RAIM even if you lose one. This is the mandatory minimum requirement for an IFR installation. After the navigation message almanac data has been downloaded, the receiver checks all satellites to determine the best available for use. The best fix from 4 satellites is with 3 close to the horizon and 1 directly overhead. Initial pseudo-ranges may be in error because of receiver clock inaccuracy. They are corrected by minimizing the size of the cocked hat, which removes the user clock bias. These are the main sources of error and the way that they are corrected where possible. User clock bias is corrected by the use of pseudo-ranges. Space vehicle geometry error is caused by the SVs not following their predicted orbit. Ephemeris error is the space vehicles not being in their predicted position due to the effects of perturbations in gravity from the Sun, Moon and planets. SV clock error is monitored by the control segment. Ionospheric error is reduced by using 2 frequencies, the L1 and L2. Multipath error is caused by reflected signals from the ground or buildings. Orbital perturbations can be caused by the influence of other satellites passing close by, and there will always be receiver and instrument errors in any manufactured equipment. Finally, we'll quote the 95% accuracy figures required by ICAO. Any commercial GPS will meet this specification, including the one in your car. The horizontal error is plus or minus 13 meters. Vertically, it is 22 meters. And timing accuracy is to within 40 nanoseconds of UTC. That concludes this lesson. Global navigation satellite systems are an extremely important contribution to almost every aspect of modern life, and are likely to significantly develop further in the near future.